Right, question 16, last one. This is starts off about looking at solar panels, and then we start looking at potential dividers and LDRs, how LDRs work. So, right, first up, it's intensity, isn't it? The only complication is the rays are hitting the solar panel at an angle of 50 degrees rather than 100. Right, we're given the value incident to the Earth's surface, radiation incident at the surface of the Earth. What that means is at right angles. Okay, so 1,100 watts per meter squared. Right now, that's the value of the intensity in this direction. That's the intensity of these rays. Okay, we want the intensity of light in this direction. Okay, so we want the components. Yeah, we need to kind of resolve. We need to include a trigonomic factor. Okay, now is it going to be sine or is it going to be cos? Right. If the light was coming in at right angles, like the red ones, then this angle would be 90, wouldn't it? If the light was actually going in that direction, i.e. parallel, then the angle will be 0. So it's going to be sine, isn't it? All right. These rays, the red rays, are going to be sine 50. Okay. So we're kind of resolving. We're kind of finding a component, okay, of the blue rays. Right. So if this angle here is 50 degrees, this angle here is going to be 40 degrees. Yeah. So this red ray here is going to be cos 40 or sine 50. So we're using sine 50. Right. So the intensity of light incident on the solar cell, okay, the intensity of light is the 1,100 times sine 50. So the intensity incident on the solar cell is, let me just calculate that. 842. Okay, 843. 843 watts per meter squared. Okay, right. So now we know intensity is power over area, so we can work out the power in, can't we? So the power in is equal to the intensity incident multiplied by the area. Now the area is 2.4, isn't it? 2.4 meters squared? Yes. So the power, so times 2.4. So the power in we've got is 2022 watts. That's the total power into the solar cell. Right, now it's not 100% efficient. In fact, it's 20% efficient. So the power out is power in multiplied by the efficiency. So we've got an electrical power out of 404 watts. Okay, right. Next up, we've got a potential divider. We have an LDR in a potential divider. Now we want it to switch on a motor, don't we? Right, now the output is taken across the fixed resistor. Okay, now the output needs to get up to, so the motor is going to go here. The output needs to get up to 13 volts for it to switch on. So we need to calculate the voltage across the 1 kilo ohm resistor when this resistance is 750 ohms. So it's a potential divider, so we're going to use our potential divider equation. Right, so V out across the fixed resistor is going to be a share of the input, isn't it? Now, the share is how much of a share the resistance is of the total resistance. But we've got 1,000 ohm, we've got 750, so the total resistance is 1750. Okay, now the V in this case is 24. Okay, so that's given us an output voltage of 13.71 volts. 13.71 volts. Deduce weather, so you can't just leave it there. You have to say, yes, motor will switch on because this value is greater than 13 volts. Okay. Finally, right, when the LDR is incident, when light's incident on the LDR, electrons move to a higher energy level where they become conduction electrons. This is because the resistance to the LDR causes the resistance to decrease. The student says this is the photoelectric effect. No, it's not. The student's incorrect. By compare and contrast the photoelectric effect with the effect of incident radiation on the LDR. Okay, so it's similar. It is similar, but that's what we need to talk about. Okay, right. If you remember, semiconductor devices like thermistors and LDRs work because they contain a semiconductor. A semiconductor is a material that sometimes conducts electricity well and sometimes doesn't, depending on external conditions. Okay, that's all to do with this diagram here. If you remember, it's all about conduction bands, band theory. All right, in metals, the conduction band and valence band are always, crikey, always overlapped. In insulators, the gap between the conduction band and the valence band is always too high for electrons to jump across and join the conduction band. But with semiconductors, that gap is just small enough so that electrons can, if they get enough energy, jump into the conduction band and join the conduction party. Right. It's also how LDRs work. So thermistors do this, but LDRs do it as well because the light comes in. So this is the semiconductor here. Okay, so instant light will come in, electrons will absorb photons, and they will make this jump. Okay, each electron will absorb a photon and make a jump into the conduction band, and then they can then conduct. And these electrons will conduct, okay, across the gap between the two metal contacts. Okay, so that's how LDRs work. Right, similar, but not exactly the same as the photoelectric effect. With LDRs, we use a semiconductor, and the electrons stay within the semiconductor. But with photoelectric effect, this happens with metals, and the metals liberate electrons, but the electrons escape the surface of the metal. Okay, so quite a few similarities, but quite a few big differences there. Electrons still absorbing photons and gaining energy, but with the photoelectric effect, they escape. With LDRs, they stay within the semiconductor. There you have it. Question 16 and paper 2, done and dusted. Thank you very much.